This is Jiaxin and from the Ohio State University. I'm very honored and happy to get invited to give a talk on the MoRN seminar. Today, I'm going to talk about the algorithms for finding weakly reversible and low deficiency realizations upon the polynomial dynamical systems. And actually, this is the joint work with Gheorghe, Abhishek, and Polly. Thank you. Well, let's go. Today's talk, I will separate into 4 parts. First, we will quickly going through the chemical reaction network. Then we will talk about the uniqueness on weakly reversible and differential zero realizations. And on the third and fourth part, here I want to say WR0 means weakly reversible and differential zero, while the WR1 means weakly reversible and differential 1. So on the third and fourth part, I will talk about algorithms for WR0 and WR1 relations. Okay, let's go. Okay, I will quickly go through it because I believe everyone here is pretty expertise in this. Like the standard deterministic model of the mass action kinetic means if you have a reaction occurs, the reaction rate is proportional to the concentration of the reactant. For example, if you have X1 plus X2 goes to X3, then the reaction rate should be X1 times X2 times the K, which is granted as a reaction rate. And mathematicians want to have a nice plan to demonstrate this reaction network. And the one tool is called Euclidean embedded graph, whereas we consider every reactant and product space or complex as the vertices on the graph. Meanwhile, the edges connect to vertices on the graph is representing reactions in the chemical reaction. So this is examples. You can see we have pretty many complexes, Y1, Y2, up to Y6. And we can put it into the species plane, X1, X2 plane. And we have several edges and vertices. Okay, and after we are granted the K as a vector of reaction rate constant, we can build so-called mass sections kinetic system, and we can find its associated dynamical systems. You can see this one. Okay. You see this one, we have left-hand side is dx over dt. The right-hand side is summation of the all reactions, where the first part, the k times x to the y power is standing for the reaction rate, while the second part, y prime minus y, is standing, okay, if once this reaction happens, we have one more y prime and we have one less y. So that is the difference of y's on the right hand side. So this is how we say associated dynamical system on mass actions. Okay, this is examples. We have 3 reactions and we have y1, y2, y3, and starting from each of them, and we can build 3 terms, and adding them together, we have our right hand side. So this is a classical setting of mass action. Then let's quickly recall some very classical definition. First is about stoichiometric subspace. It is a vector space. It's a span by every possible reaction vectors. You can see S is equals to span of y prime minus y as long as y goes to y prime is in the graph. So it's a collection of all reaction rates in the graph. And also we introduce a very important index, which is called deficiency. We will talk about more later. And here, deficiency is defined as the numbers of vertices minus L, which is representing the numbers of connected components, minus S, which is the dimension of the stoichiometric subspace. Next, we will introduce what is a linkage class. So linkage class is just a connected component. And when each connected component is strongly connected, which means every edge is at the part of cycle, then we call the graph is weakly reversible. And also, we can define associated vector space on each linkage class. Let's say, if we just collect the reaction inside of one linkage class, we call it, this is associated vector subspace by this linkage class. Moreover, if this linkage class, the vertices in this linkage class are affine independent, then we call it, it is affine independent linkage classes. Okay, this is the very classical definition. So let me quickly go through them. This is an example showing like in the XY, X2 plane, we have, one connected component, one linkage class. It is weakly reversible, and deficiency is equals to the 4 vertices minus 1 connected component minus 2 equals to 1. So this is examples of deficiency. Okay, now I need to explain a little bit in details about the following two concepts. First, I want to introduce what is the net reaction vectors. So if you look at the right-hand side of mass action system, each term has two parts, k times x to the y power times y prime minus y. So if you look at the monomials, you can see on each monomials, it is corresponding to one vertex. The net reaction vector is saying, if you focus on each vertex yi, and we collect all the reactions starting from it, you can see, we collect all the reactions starting from yi, and do the summation of all the kij times yj minus yi. If you do this summation, we call it net reaction vectors. So clearly, it is just the output of the effect from the vertex yi. As long as you let it times x to the y power, it is exactly the part on the right-hand side of mass action kinetics. Okay, but this is kind of the properties on the vertex yi. So yeah, it is a very important property. We will use it later. And of course, after we pile up this y1 to yn, n means the numbers of vertices in the graph, then we get so-called a matrix of the net reaction vectors. Next, the second pretty important concept we will talk about is dynamical equivalence. So what is saying to be a dynamical equivalence between two systems, gk and g prime, k prime? Simply speaking, it just means for every y0 vertex in union of two vertices set, the right-hand side, the corresponding right-hand side is the same. You can see both red underline term is the part of the right-hand side of mass action systems related with the vertex y0. So if you have the same this left equals to right on all vertex, that is kind of telling you, okay, two systems has the same right-hand side. Therefore, it is very intuitive to say they are dynamical equivalents. And moreover, since it is equalities on just vertex y0, of course, following the mass action kinetics, you can cancel by these two, of course. After cancellations, you will find, in order to say two mass action systems being dynamically equivalent, it is equivalent to say this new left-hand side equals the right-hand side, and we can translate into the language of the net reaction vectors, which is this. I think this is making sense. Okay, so that is telling us if on every vertex on both systems, as long as we guarantee the net reaction vectors is the same, then we can say both systems are just almost same. They are dynamically equivalent. Okay. So this is an example of dynamic equivalence. We have a left-hand side and right side graph. And the only difference is the right part, we have these two reactions, But you know, these two reactions, one is going up with K prime, one is going down with K prime. If you can consider the right-hand side, it will give you the zero part. So the right-hand side, they are the same, so they are dynamical equivalents. So this is a very straightforward examples of being dynamical equivalent. Okay, so now let's go to the interesting part. Actually, I think this is a consecutive story. I think the story is beginning like one day, me, George, and Polly are just sitting down talking about, I think George and Polly find a uniqueness of relations on a weakly reversible difference zero in a single linkage class case. Then we just discuss, okay, whether it can be generalized into arbitrary linkage class. Then we just work and keep working. We find the uniqueness of that. And then we find maybe it's not enough to get just uniqueness, because we know the existence is always bounded with uniqueness. Then we just keep going to find an algorithm for the WR0 relations. WR0 means weakly reversible and difference zero. And after that, we want to see like whether we can do any generalizations on such algorithm. Then I talk with the Abhishek and we find an algorithm for WR1 relations. So that is the whole story. And let's start from the first part. First, we will talk about the uniqueness of weakly reversible difference zero network. And for simplicity, we just call it WR0 network. Yes. Okay, and why we are so curious about uniqueness and algorithm on WR0 network, the basic reason is coming from difference zero theorem found by Martin Feinberg. In the theorem, it says, if you give me a difference zero in Euclidean bed graph, if this is weakly reversible, then the system is so-called automatically complex balanced and is always at the mid positive steady state within each invariant polyhedron. So there's many wonderful properties on the complex balance system, you know, like locally stable, like a lot of nice theorem about that. So that's the motivation we want to look into the WR0 network. And first, we start to find the necessary condition for being a unique WR0 relations. So the following two examples will show, if you give me a dynamical system and you say, if this dynamical system has a unique relations, so it needs weakly reversibility and difference zero. So the first example you can show, two systems, graph A and graph B, they are dynamical equivalent. However, they are not the same, right? It is not a unique way to representing this dynamical system. So we can see the weakly reversible is pretty important because they are both difference zero. In these examples, it is saying like, if you give me a dynamical systems, although both are weakly reversible, however, the right part, the difference is one. So it will give you another relations upon this associated dynamical system. So these two examples is telling us to find a unique relations, weakly reversibility and difference zeros are pretty important. So the key lemma to find the uniqueness is to say, if in this linkage class, let's assume we have just one linkage class, and if you just focus on the net reaction vectors starting from each vertex in this linkage class, then you will find if this graph is weakly reversible, the span of the net reaction vectors is equivalent to the stoichiometric subspace. Moreover, if this G is difference zero, then we have more. We can say, if we just delete one of the W, let's say we delete W1 1, then the rest of m minus 1 vectors, they are all linear independent. So which means actually any m minus 1 vectors from these m vectors, they will automatically form a base for this S. This is the key lemmas. And use these lemmas, actually we are able to show, first, let's say, if you give me a WR0 relations with a single linkage class, it should be, has unique relations. The reason is, if you have a WR0 relations, the linkage class should be alpha independent. So actually there's no free space for you to going around from relation A and relation B's, because the dimension will restrict the linear dependency between the W1 to Wn. Therefore, if you have two different relations, then at least one of them should break this deficiency equal to 0. Like it will break the linear independency. Or by the way, I think a similar result has also been proved in another paper with by George, Polly, I think Matthew and Gabo, etc. Okay. So using the same idea, we can show if you want to have a WR0 relations, it has to be unique. The idea is pretty similar because being a WR0 relations, it is saying within each linkage class, it is alpha independent. And the stoichiometrics on each linkage class, let's say S1, S2, S3, they should be also linear independent. So if you have two different relations, it will break this linear independency. That is the idea why we can find uniqueness on WR0 relations. Okay, now let's go to the algorithm to finding a WR relations. So if you look at this flow chart is made by Polly. It's a very nice flow chart. So imagine we have a dynamical system and we have our right-hand side. Then by looking at the monomials and the right-hand side, we can first derive the vertices. This flow chart is telling us if you collecting the monomials and the corresponding net reaction vectors and the matrix of the net reaction vectors, then you just need to figure out the generators of the cone of the kernel W intersect with the positive oscillation. Then use these generators, you just need to look at this support. The support of these generators will give us which vertices are belonging to what kind of linkage class. Okay, so let's quickly explain why it is making sense. We know a very famous decomposition of mass action kinetics, dx over dt, could be written as y times the Kirchhoff matrix AK times the nu x, or we can say x to the y power. Here, recall like the net reaction vectors is a collection of a reaction on each vertex. So by a very quick computation, you will find W is actually equals to y times AK. Therefore, the equation could be rewrite as this. So you just need to figure out what's the kernel of W to make this dx over dt equals to 0. And moreover, if the system is WR0, we have W equals to YAK, and YAK's kernel is equals to AK's kernel. This is because we know if it is differential 0 and weak reversible, or steady state is a complex balance steady state. So they are the same. So if we want to just focus on the kernel of AK, we can just directly look at the kernel of W. And by computing W, we know the information of the kernel of AK. And what kind of vector could be the kernel of AK? This theorem in one of the Feinberg's paper is telling us If AK is the Kirchhoff matrix, then there exists a base C1 to CT where each C vector support is corresponding to one terminal strong linkage class. Of course, if in a weakly reversible case, the terminal strong linkage class it indeed collide with each linkage class. Therefore, as long as we figure out what's the kernel of AK or we figure out what's the kernel of W, we can find a linkage class. Okay, this is the key idea. And using this key lemma, we are able to show the kernel of W intersect with the positive oscillant, the minimal set of generators for such cone has L element whose support is corresponding to the linkage class of G. So of course, this is under the assumption of this system, this dynamical system admit WR0 relations. So this is the key lemma for the algorithm. Now we see examples. Think about if we have this dynamical system, you can easily see we have monomials x1, x2 square, x3 square. So we have y1, y2, and y3. Then you can get the net reaction vectors from the right-hand side. It is -3 to 4, 1 minus 6 plus 4, 2, 4 minus 8. Okay, then you can build your net reaction matrix. Then we can find generators and we can test this generator support is 1 to 3. So the linkage class should be a single linkage class whose support is 1 to 3, exactly y1, y2, y3. And then you check whether each net reaction vectors could be realized within that linkage class. The answer is yes, because this is good examples, right? So we find such a good WR0 relations. The picture is here. Apparently it is different 0, right? Okay, so this is a story for algorithm to WR0 network. Let me use the very quickly going through how to find an algorithm for WR1 relations. So first, why WR1 network? It is interesting. It is the weakly reversible and deficiency 1 relations. And again, from Feinberg, we have famous deficiency 1 theorem. It is saying if it satisfies the deficiency smaller or equal to 1, sum of the deficiency is equal to the whole deficiency, and it is, let's simplify as weakly reversible, then the system is able to have one positive equilibrium, and it is the unique equilibrium within each stoichiometric compatibility class. So this is very interesting and nice. Therefore, we want to figure out an algorithm to a WR1 network. And the difference between WR1 and WR0 is now it could be possible, like the whole deficiency is not equal to the sum of the subdeficiency. And here we call, if the whole deficiency 1 is equal to the sum of the subdeficiency, we call it type 1 network. It is exactly qualified for the application on the deficiency 1 theorem. And we call the deficiency is bigger than the sum of the subdeficiency, we call it type 2 network. It is not qualified, but still we can say something about the multi-stationarities on this type 2 network. Okay, then when deficiency equals to 1, the kernel of W is no longer coincide with the kernel of AK. Actually, it has 2 parts. Kernel of AK and kernel of Y intersect with the image of AK. And I referred a paper written by Karadi and some other authors. They call this first type of kernel, the corresponding generator is called acyclic generators. And second type is called stoichiometric generators. Again, you can see we want to figure out how these generators can lead us to find the linkage class. Okay, First, this quick lemma is saying, if you have a single linkage class weakly reversible systems, there's a relation between the numbers of generators and deficiency. And moreover, if you give me a system with deficiency 1, the generator number is 2. I want to say, like, when the deficiency is 0, the number of generators is 1 because it is one-dimensional. Using these properties, we can find the key lemma of what is the minimum generating set of this kernel W intersect with the positive OSINT. For the type 1 network, there exist L plus 1 vectors where the first L minus 1 vectors give us a linkage class, while the last 2 vectors, DL and DL plus 1, give us a final linkage class. If this system is in a type 2 network, we can find L plus 2 vectors as the generators, while the first L vectors is giving us a linkage class, while the last 2 generators is kind of have support everywhere. Therefore, we can again use these generators to find what is a good linkage class. And this is the flow chart. So you can see, we can just randomly pick 2 generators and look at the rest of them, and then use this rest of the set of generators to build the linkage class. And then we can check whether it is realizable or not. Then upon the result, we can figure out we have a type 1 network or type 2 network. This is almost done. Finally, we are able to show in the WR network, there also exists some uniqueness. In the same project, we are able to show if you give me a mass action systems, it cannot have both type 1 relations and type 2 relations. So somehow in the term of type, it still keep the uniqueness. Yes. Okay, so that is the part for the WR1 network. So for the future problems, we are seeking for a generalized algorithm on a network which can be worked on deficiency 1 theorem. Because if you familiar with deficiency 1 theorem, actually the whole deficiency is not need to be 1. It is kind of a summation of 0 and 1. So it could be very large. And also we want to find a generalized algorithm on a weakly reversible network, because being a weakly reversible is still very nice to the right-hand side, to the whole system. Okay, these are the future problems. And these are the papers I cite during this talk. And thank you.